Okay, so to introduce myself, my name is Nazar. I've been working with Dr. Branham over this past summer for my plasma internship. This presentation, I'll just give an overview of what I did, what I accomplished, what I was doing, what I will finish by hopefully the end of the next 2 weeks. So yeah, I guess I'll just start. So my work was roughly divided into 2 parts. First part was just the experimental hands-on experience, and second one was a little more theoretical. It's not purely theoretical. I will explain what it means later on. For now, let's start with the experimental part. My responsibilities were mainly concerned with the chamber that was supposed to run the LIF diagnostics, which is a way to measure plasma parameters inside of a Hall effect thruster, which is the setup that I was working on. And it's really just as simple as you pulse a laser into the plasma, you record the radiation that comes out of it, and you analyze it, and from that you can deduce the plasma parameters. So my responsibilities were to run the vacuum chamber, which the Hall effect thruster has to be run inside of a vacuum chamber, was to run the thruster itself, and then to help with the laser running and data collection. And in the meantime, when something was not working, something needed to be fixed, I would also help with that. So I think the best way to show what I was doing is just to overview the setup itself, what could go wrong, and then to overview some of the things that I did specifically. So the first part of the setup is the vacuum chamber inside which the Hall effect thruster is run. The chamber is quite big, even though the thruster itself is way smaller than that. That's because we need very low pressure. And to make that pressure possible, we use vacuum pumps. In this chamber, we were supposed to use 3 pumps, but one of them was out of order at the time I arrived, so we used 2 of them. One was the so-called mechanical pump, which which usually can allow us to create high pressure vacuum, but we need lower pressure than that vacuum pump can allow. So we use a second one, the cryo pump, which allows us to achieve pressures on the order of 2 times to the 10 to the -6 torr, something like that. So my job was essentially to come in every day, pump the chamber down, which is to start the mechanical pump, wait until the pressure comes down, then start the cryo pump, wait until the chamber is completely vacuumized, so to speak, and then to run the pressure gauges, see if the pressure is on the right scale, on the right order of magnitude, and to monitor it throughout the Hall effect thruster operation. And we also had the so-called RGA, residual gas analyzer, which allowed us to see what were the contents of the remaining gas that could not be pumped out of the chamber. So my job was also to monitor that, make sure that no weird stuff was going to the chamber. Yeah, in addition to this, I also had to monitor some other parameters. The most obvious one is that all the power supplies were at their respective voltages. Nothing was going out of order in that. So this first part is really just making sure everything works properly, launching the system correctly, stuff like that. So once the chamber is pumped down, we can start the thruster operation. That is done less manually. We have LabVIEW program that controls the power supplies we need to start all of the elements of the Hall effect thruster. This is how it looks. I decided to take some pictures, show what exactly everything looks like in the lab. This particular LabVIEW controls the power supplies, which we have 4 of, 1 for each element of the Hall effect thruster, so to speak. And there is a few other programs that also control the RGA I mentioned above, the translation stage, which we need to move the collection optics. As I said, the setup is supposed to implement LIF, so we pulse the laser and then we collect radiation. So the translation stage moves the collection optics from one region of the thruster to the other, so that we can analyze the different regions of the thruster. And there were also mass flow controllers that I needed to control as well. So again, my job was to run all of this and make sure that nothing bad happens to any of this stuff. And this is what it looks like in the real life, not in the program. So we have 4 power supplies, as I said, 1 for each element, so to speak. There's 2 magnetic coils that we use to create magnetic field, which we need to run the thruster, so the thruster works. Those are the power supplies at the top. There is a power supply for the anode, which is an element of the Hall effect thruster itself. There is 1 power supply for the heater, which we need to launch the thruster. We really needed to heat up the cathode, which is, there's 2 big parts of the Hall effect thruster, the cathode and the anode. So the heater, we need to launch the cathode, which then will launch the anode after the cathode is on. So yeah, again, my job was to make sure that none of those voltages go too high or too low when they need to be high. And this is what it looks like inside the chamber. We actually have an optical window on the side of the chamber, so I was able to take some pictures. This is an old one. Here you can see that the cathode, which is the red glowing part above, in the upper part of the picture, that's the cathode running. The blue spot is the plasma that's coming out of the cathode, and the red part is where it heats up, the cathode itself heats up from the heater power supply that I just mentioned. And the thruster, the thing that's under the cathode, is currently off. So you see no plasma there, but this is what the chamber looks like once the cathode is working properly and nothing goes wrong. And then once the cathode is working, we can launch the anode, and then the thruster is fully operational. If everything goes properly and smoothly, the operation should look something like this, very steady, nothing is happening, no dynamics. This is actually not fully operational thruster yet because we haven't turned on the magnetic field yet. So you see the glowing region actually should be confined much more to the exit plate of the thruster and has to be a little more concentrated white blue. But in this case, there's no magnetic field. So all of this glowing part of the thruster is actually plasma being ionized from the cathode and the anode operation. But this is pretty much what the thruster looks like once it's fully operational. Once we achieve that, which only happens again after we pump down the chamber and then launch everything, then we can start collecting the data, which is the main focus of the setup I was working on. And that's the next part that I was working on, that I was responsible for, the data collection. So again, the method we use to collect the data is first we pulse a laser through the plasma, which is done using this laser setup. And then we collect the radiation at many locations inside the thruster. This is what the setup looks like in real life that I had to work on. I tried my best to write up all of the elements that are on the setup. I don't think you can see all of them very well, but the main element is obviously the laser, which is in the far bottom left corner. And once the laser is on, the beam goes to the right, goes through an optical schematic, of lenses and mirrors and stuff like that. Then it goes through into the ettalon and the wave meter, which are just elements we need to make sure that the laser is working properly. And to find its wavelength, it's mostly for our own purposes, not for the purposes of experiment. But then part of the laser obviously goes into the chamber. There is a orange wire that is connected to the chamber and goes into the plasma. So the laser pulses through the plasma. And then, as I said, once the laser pulses through, we collect the outgoing radiation, and that goes into the monochromator right here in the upper left corner, which is covered with a black cloth just to make sure that it operates optimally, so that there is no light interfering with it, or no dust, nothing like that. That monochromator, what it does is really just it analyzes the incoming radiation, makes it more convenient for us to work with and determine the plasma parameters from. So this is the laser setup, and it's controlled by its own power supplies, which there's plenty of. There's 2 laser controllers for our specific laser, and we need also a laser amplifier to increase the laser signal so that it's enough to go through the plasma and then go through our collection optics and still be readable, and so that we are able to determine plasma parameters from it. There is also many other elements to our setup. In the background, there is a few power supplies that we need for other elements. The tube power supply, the chopper's power supplies. I don't think there is any point to go into detail what those are for. They're pretty much mostly for our own, again, purposes of making sure the laser works correctly, as well as, the tube is for the experimental part. It's mostly for having a reference point once we collect the incoming radiation from the chamber. We have a controlled plasma inside of a tube that's powered by the tube power supply. And then we also need the lock-in amplifier for the incoming radiation, which just amplifies the signal. And we also need it for the outgoing radiation, so we have 2 of those. And all of that is run through a program. And again, my job was to make sure everything runs properly, to launch everything, and then to help with data collection, which consists of several parts. We have the oscilloscope that allows us to see all the data collection process in the real time, so we can make sure that the data is good, that nothing's going wrong. And the few parts I was saying is there's several things we collect in addition to the incoming radiation from the chamber. There's the wavelength of the outgoing signal from our laser, which we have to analyze to make sure the laser is working properly. There's also the ettalon I mentioned before that we also need to make sure that the laser is working properly. But most importantly, obviously, is the data that we collect. And we can see it on the monitor here in the LabVIEW program and on the oscilloscope. So my job was to collect the data, save it, and also in the meantime, look at it, see if it makes sense, if there is nothing wrong with it. If there is something wrong, then we have to find the problem, solve it, things like that. So this is an overview of the way we collect the data and what I had to do with it. Now, for the big picture in this project, we needed a lot of data to be collected, and realistically, we were ambitious about the amount of data we wanted to collect, and we were expecting we wouldn't have enough time, and we didn't, because there is always something that goes wrong with your system, as in all of the experimental works you can think of. And in our system, some things also went wrong, so they delayed us, and we couldn't do everything we were hoping to do. So I think it's important to say a few words about what exactly could go wrong in our system and what did go wrong and what we had to tingle with when we had to fix things. These are just the things that I could remember that, are small things, not huge problems with the setup itself, but which take time and altogether delay the process of the experiment. So let me just go over them quite quickly. The cathode, as I said, is one of the main parts of the thruster, and there's a few things that went wrong with the cathode during my time here. One was the cathode orifice became too big. That was just when I arrived. Another one was that the cathode insert had carbon on it and wasn't working properly because of that. That's the most recent issue, as a matter of fact, that we have just solved, and that took us quite a while, half a week. In addition to that, there were a few problems with the gas line. At first, when I arrived, the gas line leaked a bit, so that was actually a spectacular moment, because when the gas line leaks inside of a full effect thruster, there's plasma there, which immediately goes to the leaking gas and creates a fireball on the wire from which the gas leaks. That was spectacular, but we fixed it. It didn't take that long. In addition to that, there was a constant need to change the optical glass. As I said, we collect radiation from the thruster. We do that through a glass that's specifically inserted on this side of the thruster. And the glass is made of quartz, so it's very long enduring glass that's designed, it's not regular glass that would just deteriorate very quickly, but even that glass had to be changed almost every time we operated the thruster, every 8 hours of operation or so. So we had to do that quite often. In addition to that, there were some problems with the pumps. In our case, the pumps were actually working very well throughout my stay here, but at some point it took us about a week as well, or half a week, to fix a cryo pump issue. This is all just to show what exactly an experimental work entails. It always entails fixing a lot of issues. There is no avoiding that. I was not taking pictures, unfortunately, when either of those problems were arising. Even when the fireball was going on, I didn't have time to take the picture. So this is the only picture I took. This is the cathode insert. It looks pretty cool. It's very small, as a matter of fact. These are my fingers, actually, so it's very small. On the inside you can see it's black, on the outside it's purple, on the inside it's supposed to be purple as well. That's the time when it was covered with carbon, when we had to fix it. We did fix it at the end, as I said, but all of that takes time, and that was the main part of my stay, was to collect data and to fix the issues which were arising when we were collecting the data. And overall, we collected a lot of data. Again, the ambitions are always to collect more data, but we've achieved enough on this front. Now let me go to the second part, which was a which was a sort of secondary project, but was actually the focus of my last month of work here or so. The setup itself, as I said, was focused on LIF diagnostics. For the theoretical part, I was trying to do optical emission spectroscopy. It's a different way of diagnosing plasma inside of the thruster. The first one, in the first method, we had to pulse a laser through the plasma and collect the radiation. In this one, we just don't pulse the laser. That's pretty much the difference. And this is actually still a work in progress. I'm working on it. I hope I will finish in about a week or so, maybe 2 weeks tops. And because of that, since it's not finished yet, it's hard to give a complete walkthrough of what the work is about. But I will I have a condensed story that I think I can tell without giving any technical details that I think will give an impression of what exactly I was trying to do with this project and what I accomplished, what I will finish in 2 weeks. So essentially, in this method of diagnostics, what we do is we collect radiation without even pulsing the laser, because plasma itself always emits some radiation. And the key is that we actually can predict this radiation, and quite well theoretically. And because of that, once we measure it, we can deduce all the plasma parameters from it. And the key problem with this approach is the availability of data, because the theoretical predictions of the radiation, they depend on quite specific data sets for xenon, for example, which is the gas we used in our thruster. And those data sets have to be measured beforehand before you can make theoretical predictions. And in the case of xenon, the data was less available than for other gases like argon. So my problem was to, first of all, find the data. Well, first of all, to find the specific approach within the optical emission spectroscopy, and then find all the necessary data and implement it to deduce the plasma parameters. So this is the story that was going on with the measuring of the data that I need. Essentially, back in 1998, there was a group that found the sum of the data that we need to run this diagnostic, not all of it, and they published a very detailed, very precise, very good paper, which was referenced everywhere else. And that was my starting point. I was just trying to implement that data. And afterwards, in 2006, there was another work, which was the continuation of that one, that extended the data that was available and also somehow managed to get away with the lichen data. And they found they essentially implemented the same diagnostic that my goal was to implement, and they managed to avoid the data that they did not have available. So that's the next part, the next step of the story. And then in 2011, as a continuation of that work, back in 2006, 2 other groups of people measured 2 separate data pieces that were missing. Altogether, you can roughly say that to implement the diagnostic I am aiming to implement, you need 3 data sets or so. For accurate, but not completely complete description, you need 3 data sets. So the first one was measured in 1998. In 2006, the other 2 were avoided, and some good results were found from that. Very reliable measurements. But in 2011, 2 other data sets came in. So yeah, at that point, the model back in 2006 could be implemented even more reliably. And in addition to that, in 2011, 2013, afterwards, there was a lot of theoretical work on calculating the data sets that have to otherwise be measured. We can predict a lot of things theoretically, and the main problem with those are verification, because most of theoretical approaches require approximations of some sort. You never know how well they work, for which conditions. But there was a lot of work in that direction, and it concluded basically in 2019 when there was a paper that described all of the phenomena that you might hope to include into a model like the one I was trying to implement. And they found very good agreement with experiment. So that was basically a benchmark point for the approach I'm trying to use. But in my work, I'm going to focus on finding plasma parameters, while in 2019, the group that wrote this paper focused on finding the plasma, the outgoing radiation, if you will. They predicted the radiation based on the parameters that were already known to them because they already diagnosed it by other means. So the novelty here will be to reverse the process, so to speak, and use the reliable data that was found recently in 2019, and find electron temperature, number densities, stuff like that from that. That was never done before, so that could be quite new. And we can use it to find to study some interesting things about the Hall effect thruster itself. We can measure the electron temperature inside of the thruster now, which is also quite new. Well, some people did that before, but it is a rare direction, so it is almost new. And we expect that overall, this work should be quite good. At the same time, we see that since in 2019 this work was concluded, basically all the phenomena were accounted for, it might be time to find some more general approach to the problem. And we have a few ideas about what those could be. So overall, my work will be focused on implementing this diagnostic of plasma, as well as using the latest, most recent data sets, and possibly suggesting a slight generalization of the existing approach that could be subject of the following work. So this is a good summary of what I was doing on the theoretical part of my project. I think this is a very good overview of what I did and tried to accomplish in the past few months. For the theoretical part, I'm still, as I said, working on it. In the next few weeks, I hope to finish, possibly write a paper. It might take a little longer to write it up, but we expect the overall result from the theoretical part to be a research paper, which is very good. This is a great accomplishment for such a short time, for just 3 months of an internship, for 3 months of my staying here. For the experimental part, we have collected a lot of data, so that's also an accomplishment. Again, we could collect more. You can always collect more, but overall, I think this is a very good overview.
Hi, my name is Flasny, and thank you for watching this video. Make sure to follow us on our social media at CPHUL on Facebook, LinkedIn, and Instagram.